Continuing, working through these problems from the practice test. So these are the practice test review problems. So 15, we're given this graph of a function with lots of points marked, and they're going to ask some questions. What is f of negative 28? So you go to negative 28 on the x-axis, which I believe is right here, and the value of x, or the value of the function. So when x is negative 28, what's the value of the function? It's negative 2. And when x is negative 12, which I believe is right here, what's the value of the function? It's 3. So a couple more. When x is 24, what's the function? 24 is here, just like the function's 2. When x is 0, looks like the value of the function is negative 1. Is f of 8 positive or negative? So here's when x is 8, here's the function, looks like it's negative. Is f of negative 8 positive or negative? So here's negative 8. Looks like it's positive. Now here's what's tricky is, there's lots of more questions, but we can't see the graph. What I'm going to do, which is a little crazy, I'm going to try and sort of cut this graph out. So as we're answering these questions, sort of see it. So it will make sense. So we'll see how this works. So I think we're ready for part E. For what values of x is f of x equal to 0? So let's figure out where the function is 0. Function's up and down. Looks like the function is 0. It's like the 3 places here, here, and here. So what are the values of x? It looks like this is, I believe this is negative 24. And here it's negative 4. And then here, 16. So there are actually 3 values of x where the function is 0. So f, for what values of x is the function greater than 0? Or you could say the function's positive. This says type a compound inequality. A lot of times ask for intervals. Here they ask for inequality. So basically, we got to figure out where's the function positive. Well, it's negative here, and then it goes positive, and then negative, and then positive. Looks like there are 2 positive regions. So for this one, looks like x has to be between negative 24 and negative 4. So and then it's positive from 16 to 24. Now it's sort of interesting. For the 24, I put the less than or equal to because this is actually a positive number. Where at 16, it's actually at 0, so I cannot include x is 16. I do include it when it's 24. All right, problem G, what's the domain of F? The idea of a domain on a graph is what's the smallest value of X and what's the largest value of X, if there are no breaks or gaps in between. Looks like this graph starts at -28 and goes to 24. Type a compound inequality. Well, integrals are so much easier. So I think it should be so -28 and up to 24. What's the range? So the range are the y's, the up and down. So it looks like the smallest value of the function is at -2, and then it goes up to 3. So it should be something like that. What are the x-intercepts? X-intercepts are the places where the graph crosses or touches the x-axis. Looks like there are 3 places where the graph crosses the x-axis at -24, -4, and 16. That should be the correct answer. What are the y-intercepts? Where does this graph cross the y-axis? One place. Looks like at -1. How often does the line y = 1 intersect the graph? So if I go to y = 1, which is right here, and I draw an imaginary horizontal line, how many times does it cross the graph? Looks like 1, 2, 3. This actually continues on the next page. Lots of questions. Here's my graph still. Oh, I think the question started. How often does the line x = 1 intersect the graph? So the line x = 1 is pretty much in here someplace. You can see it's going to intersect the graph just once. For what values of x does f of x = -2? So let's go find on the graph where the function equals -2. Looks like -2 is right here. So we got right here and right here. So the 2 values of x, -28 and 8. And the last question, for what values of x does f of x = 3? So where's the function 3? Right here. There's one place on the graph that happens. And that's when x is -12. All right, so that's just interpreting a function as a graph. 16, same kind of thing, lots of questions. To determine whether the graph is out of a function by using the vertical line test. If it is, use the graph to find, okay, all this stuff. So first question, is the graph a function? Vertical line test, you draw vertical lines. If it crosses the graph in 2 places, it is not a function. Hopefully you can see here, vertical line only crosses the graph once, so yes, it is a function. Excuse me, I think I'm going to sneeze. Okay, sorry about that. Next question. If the graph is out of a function, what are its domain and range? You notice here it's got arrows on the end. So for domain, which I'm looking at values of x, what's the smallest? What's the farthest this graph goes? To the left? Well, it goes to negative infinity. What's the farthest it goes to the right? Infinity. So the domain, hopefully I can write it as an interval this time. Negative infinity to infinity. Now the range is the up and down. So as an interval, what's the lowest? What's the farthest down where I have a graph? Well, right here, right? This is where the graph starts. And that's when y is -4, and then it goes up further. So it should be, you include -4, bracket, -4 into infinity. If the graph is out of a function, what are the intercepts? Hopefully we can still see. Intercepts, x-intercepts, where the graph crosses the x-axis. Looks like it got one here and one here at -5 and at -1. So -5 and 1. Now when I look at the up, look at type as an ordered pair. Sorry. That's interesting. I did the x-intercepts, but they want all the intercepts here. So these are the x-intercepts. The y-intercept, there's one y-intercept. It looks like it crosses the y-axis when y is 5. So it looks like there are 3 intercepts altogether. Then read the last question and we can look at the graph. If the graph is out of a function, determine what kinds of symmetry it has. So symmetry is usually where it's symmetrical around the x or y axis or the origin. So if you look at this, here's the x-axis. If you flip this graph, and it's almost like if it rotates around the x-axis, if you rotate it, it's not going to be the same. If you rotate it around the y-axis, it's going to flip like this. It's not going to be the same. I'm saying D. It's not symmetrical anywhere. All right, 17. Another problem with a graph. Use the graph of the function f given below to answer the following questions. So here's this graph. List the values of x at which f has a local minimum. Select the correct choice below and fill in any answers. So the minimum is like a local minimum, sort of like, it's like a valley. Maximum's like a peak or mountaintop. Minimum's like a valley. So if I look at this graph, this is a local max. It's like the top of a hill or mountain. But I come down, so here's a minimum. It's like the bottom of a valley. Another maximum, another minimum. So there are 2 minimums. So they're saying listed values of x where you have a local minimum. So this one right here looks like at -1. And then over here, looks like it happens when x is 3. Then it says, what are these local minimum? If they exist, select the correct choice below and fill in. The local minima are, I'm not even sure what it's getting at. Let me reread this. What's the difference here? Select the correct list the values of x at which if that's what. Oh, I think what they're saying here is at these minimums, what's the value of the function? So here I gave the value of x, and here it's saying, okay, so at these minimums, what's the actual value of the function? And it's actually, they're both the same. The value of the function is both -1, or you could say the value of y. So the value of y at each of the minimums is -1. That seemed to be worded very well. All right. Another graphing problem. Lots of these. So here's a graph. And they sort of tell you you're going to find intercepts, domain and range, intervals, blah, 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 blah. All right, let's just go through this. What are the intercepts? Intercepts are where the graph crosses or touches the y-axis. They want ordered pairs. So here it touches the x-axis, crosses the y-axis, and touches. Looks like there are 3 intercepts. And the first one looks like -2, 0. This one is 0, 1. And this one is 2, 0. Domain and range, you notice there's no arrows on the end, so it starts here and ends here. So it starts at -3 and it goes to 3. So as an interval, I can, oops, I should include with brackets. -3 to 3. And then the range up and down looks like the smallest is 0, and it goes up to 2. Check as I go along, make sure I'm not getting confused and making a mistake. Those look correct. Now, I'm probably going to do what I did on that other problem, just to make it simple. I'll just sort of. So we can keep looking at this when we're trying to answer the questions. We're down to C. If I can stick it up here. On which intervals is the graph increasing? So increasing is as you move on the graph from left to right. If it's going down, it's decreasing. If it's going up, it's increasing. So here, it's decreasing, then increasing, then decreasing, increasing. So where is it increasing? Looks like it's 2 places where it increases. And what you do is the way you indicate this region is by an interval. You look at the values of x. It starts when x is -2, and it increases until x is 0. And then it starts again when x is 2 and increases till x is 3. So it looks like interval notation. So where is it increasing? So it starts increasing, starts from -2 to 0. And then from 2 to 3. On which interval is the graph decreasing? decreasing, it looks like -3 to -2. And then 0 to 2. On which interval is the graph constant? So a constant means it would be perfectly horizontal. Well, the graph is never horizontal. So you'd say the graph is not constant on any interval. Then the function is odd, neither odd or even. So this one, you look, once again, if you think about the y-axis as like a pivot, and you sort of flip it, then you know what? It looks the same. Another way to think of this is like a mirror image. If I look at this side, it looks like this, and this side, it's like a mirror image, basically the same. And when it's symmetrical around the y-axis, that's called an even function. Symmetrical stuff is a little strange, but anyways. All right, 18. Going on, it's like another graphing problem. All right, use the graph to find the numbers at which local maximum. So here's the stuff. Let's actually go through where they actually ask for the questions. Select the correct choice and fill in answer boxes. The value of x for which f has a local maximum is. So it's asking, where's a local maximum? The local maximums, I believe the way they define it is just where it's like a mountain peak. So even though these are, we call these the like these would be called the absolute maximum because of this whole graph. These are the highest, but for it to be a local maximum, it has to be like a mountain peak where it goes up and comes down. So there's only one local maximum, and it occurs when x is 0. The local maximum r, so now it's saying, okay, this is where it's confusing. It's saying now at that maximum, what's the value of y? So the maximum is here, the value of y is 2. And then it says, now it's looking for local minimums. So those are like valleys. Let's go back. Are there any local minimums? Right here and right here. Looks like they occur when x is -1 and 1. So it occurs when x is -1 and 1. And then it asks at those local minimums, what's the value of y? Looks like it's right here on the x-axis, so it's 0. All right, not too bad. Now we're ready for problem 20, another graph problem. So here, so I think it's gonna once again ask about, now here it's gonna be absolute max and absolute min and local max and local min. So once again, local max and min are a valley or mountain peak. Absolute are like, can also be the ends of the graph. So this first one, the absolute maximum. So basically you look at this whole graph and see at what point is the absolute highest on this graph. Even though this is a local maximum, it's not the absolute highest. Let's look at the highest. This point over here is the highest. So the absolute maximum is at 1,6. So basically in function notation, x is 1, so it's like f of 1, and the function itself equals 6. That's the way they want you to write this. And then they ask about absolute minimum. So if this whole graph, what point is the absolute lowest? It's down here. And it occurs when x is 6 and its value is 2. So you say f of 6 equals 2 for the absolute minimum. Now the local maximum, so the local is like a mountain peak where you've got both sides. So this is a local maximum. It occurs at 3, 5, so x is 3 and y is 5. So the local maximum f of 3 equals 5. And then finally, I think they're going to ask about a local minimum. Like, are there any valleys here? Yeah, there's one. It occurs when x is 2 and the value is 4. So f of 2 equals 4. All right, 21, piecewise function problem. Hopefully not too difficult. Piecewise function f of -3. So what you do is, since x is -3, you have 3 different functions here, and whichever function you use will be determined by the value of x. So the first step for these piecewise function problems are to see what your value of x is, and based upon that, to see which of these 3 functions you're going to use. So if x is -3, my choices are x less than 0, x equal to 0, x greater than 0. Obviously, if x is -3, it's less than 0, so I'm going to use this function here. So I plug in -3 for x, so -3 squared is 9. F of 0, so now let's figure out which function we use. Well, here, the middle one is the one you use if x is 0, which is what we have. So if I use the middle function, it turns out there's not even any variables there. It's just always going to be -2. And then f of 3. So I need to use this last one because this is what you use if x is greater than 0, which 3 is. So I plug in 3 here. 3 times 3 is 9 plus 1 is 10. So it should be 10. All right, 22, moving right along. Another piecewise function problem. So, just to keep from being distracted, we'll cover up these other problems. So piecewise function, I got 2 functions. Looks like I'm looking for value of the function at 4 different values of x. So the first value of x is 0. So let's see which one it is. This one is what you use when x is between or equal to -5 and 4. So that applies to 0. So you plug in 0 for x and you get -2. F of 1, so x is 1. Looks like it's also this first one because this is when x is from -5 to 4. So plug in 1 into here, you have 5 minus 2, which is 3. Now when x is 4, now you notice this is from -5 to 4, but it includes 4. This runs from 4 to 5, and it includes 5, doesn't include the 4. So if you're doing 4, it's still got to be this one. So you plug a 4 in, and that's 20 minus 2, which is 18. And then the last one, f of 5. So now we go down to the second function and you plug in 5. Wow, 5 cubed. 5 times 9 is 125. 125 minus 4. Seems like a big number, but those are correct. All right. One of my least favorite parts of this class, these transformations and stuff. So this is initial function. We're going to do 3 things. So each of these 3 things we do is going to change this function. So once again, if you want more clarification on that, you can watch the videos. Here, I'm just going to try and solve the problem. So if I start out with square root of x, when you shift it up 3, means you add 3. Now when you reflect it around the x-axis and then reflect around the y-axis, so it's 2 things. Reflecting around the y-axis, you actually go in and just put a negative sign in front of your x. And then if you reflect it around the x-axis, you make the whole expression negative. So let me just, once again, I'm not going to take the time to explain it. So if I make the x a negative, so that takes care of reflecting around the y-axis. Now, if I want to reflect around the x-axis, I take this whole thing and make it negative. And probably in the answer they give you, they probably don't want these parentheses, so you distribute the minus, and you probably, maybe they would probably like it to look something like this. All right. '24, starting with the graph of a basic function. Graph the following function using techniques of shifting, compressing. So you know what? Especially this one, my advice, especially if this kind of problem's on the exam, I mean, fine, you can use shifting, compressing, stretching stuff, but sometimes that makes it a lot more difficult problem. Just sometimes in math, you do a bottom line kind of thing. This problem is actually going to be much easier if I just graph it. So what I'm going to do is I'm going to do the old-fashioned, and on the exam is sort of bottom line, so you have the right graph. I'm not going to really care about how you came up with that graph. So I'm going to just try and plot some points. So for example, I'm going to, I look at this a little bit and I try and pick some points that sort of make sense. Maybe it'd be easiest if I chose x equal to 3, 3 minus 3 is 0, and it makes it pretty easy. As a matter of fact, if I choose x equal to 3 and plug in 3 for x, that whole function turns into 2. So I can now plot my point 3, 2. And this is going to be a parabola because this is a quadratic equation. Now, if I want to be smart, how about my goal is to make the whole parenthesis equal to like 1. So if I set x equal to 4, right? So if I had 4 for x, 4 minus 3 is 1, 1 squared is 1. So 5 times 1 plus 2 looks like 7. So 4. Now let's do the same thing. Let's try and make the stuff inside the parentheses equal to minus 1. So if I said x equal to 2, 2 minus 3 is negative 1, negative 1 squared is 1 times 5. So actually, if I said x equal to 2, y is 7 again. Now with these 3 points, it's going to be a parabola, pretty skinny. My picture's not the best. It looks something like that. So if you want to use this, the hard thing about the shift transformation is this: when you multiply by 5, that means you stretch it times 5, and that's hard to sort of grasp. It's hard to graph that, so I just did this. The domain, this keeps spreading out. So it's going to be negative infinity to infinity. The range, it's like it starts at 2 and goes to infinity. All right, 24. I got like 5 to go. Let's see what these are like. So this is a problem where they gave you a function and they're going to ask you a bunch of questions about this function. Analyze the polynomial function f of x equals x squared minus times x minus 3. And they're going to ask you a bunch of questions. Well, one of the things we might need to do, so I'm going to do it right now, is going to multiply this thing out, because there are certain questions they ask you which you don't want to have parentheses. So you multiply it out, you get that. Matter of fact, the first question, determine the end behavior of the graph of the function. The graph f behaves like. End behavior means the whole idea if you just look at the leading term, you look at the term with the largest exponent on the variable. So you ignore the 3x squared. So basically your function, when your x's are super big, either positive or negative, is going to look like x cubed. In other words, the 3x squared sort of gets dwarfed, it sort of goes away. Next question, find the x and y intercepts, the x-intercept. So the way you find x-intercepts is you can also, even though this is f of x, sometimes for some of these questions, it's easiest to think about y instead of f of x. So here is factored, here's not factored with the y's. Because the way you find the x-intercept is you set y equal to 0. So if I set this equal to 0 and solve it, I want to look at the factored version, and the solutions would be x is 0 and x is 3. So the x-intercepts are, do they want points, or I think they just want the values of x. Yeah, x-intercepts at 0 and 3. Y-intercept, to find the y-intercepts, you take your equation, you set x equal to 0. Maybe I'll use this. If I set, put in 0 for x, what's y got to be? 0. Determine the zeros and their multiplicity. Well, you know what zeros are? Zeros are the same thing as x-intercepts. So when it says find the zeros, it's the same as x-intercepts. I already found it. So the zeros are 0 and 3. Now multiplicity means, in other words, I look at the factored form. The 0 comes from this factor, x squared. And I look at the exponent. Since it's 2, I say the 0, when x is 0, the multiplicity is 2, right? So the 0 came from this part of it, and since there's an exponent of 2, I say the multiplicity is 2. So the zeros are the same as the x-intercepts. Now it says the lesser zero of the function. So of these two zeros, the lesser one, which is 0, and since 0 comes from the x squared, it's a multiplicity of, the lesser 0, which is 0, has a multiplicity of 2, because that's the exponent. Now, when your multiplicity of the exponent's 2, that means if it's an even numbered exponent, it's going to touch the x-axis and then bounce up again. It's not going to actually cross the x-axis. It just touches it and then it goes back. So the graph of the lesser 0 multiplication, the graph of, and I think the wording they use is it touches, it doesn't cross it, it touches it. And then, so the graph of F1 touches the x-axis at x equals 0. The greater 0, which is the 3, has a multiplicity now. The 3 comes from here. And if you look at this parenthesis, the exponent is just 1, so the multiplicity is 1. So that the graph of f of f of 3. So since the exponent's 1, it's going to crosses the x-axis at x equals 3. Sometimes it's hard to interpret exactly what they're asking. And then finally, they say, determine the maximum number of turning points. Turning points is determined by the largest exponent on your variable. If it's 3, the turning point is always 1 less. So if your largest variable on the exponent is 3, the turning points are going to be 2. Now we can't see it very well, but now they say, based on all the stuff you've learned, here are 4 choices, which is the graph of this. Well, I just use process of elimination. In other words, I know, for instance, x-intercepts are 0 and 3. Look here, like this one doesn't have, even though you can't see it well, there's no 0 and 3 x-intercept or here. It's got to be one of these two. And if you look, what is the how about I ask myself when what happens when, like, let's just plug in a number, like when x is 1. If x is 1, this would be like a negative number because it's going to be 1 times negative 2. You look at this one, it's hard to tell, but when x is 1, you can see the function's positive. Here it's negative. Based upon that, the graph is A. Oh. I think this refers back to, I think somehow the printing got messed up. It should have been up there. I don't know what that is. All right. 26. Here they give you a rational expression and ask you some questions. So this is like a fraction. -3 over x plus 1. So let's say graph it using transformations. I'm not going to do that. I'm just going to graph it. You got 4 choices here. Let's see which one looks correct. they're going to probably ask about this, but I know there's an asymptote of -1, a vertical asymptote. I can see for C and D, the asymptote is not -1, it's like a +1. So it's going to be A or B. Pretty easy to check. Let's just stick in a positive number for X, because this graph says it should be positive. This graph says it should be negative, I think. So if I plug in like 1 here, -3 over 1 + 1, -3 over 2 is like a negative number. My guess is it looks like the graph. Now a bunch of questions. What's the domain of the given function? Well, if I look at the graph, you can see the domain -infinity, but there's going to be a break or a gap here when x is -1. So the domain is not going to be -infinity to infinity. It's going to be -infinity to infinity with the gap at x equals -1. So let's see. So here's the form they're saying. X is a real number. That means the domain is all real numbers except x cannot equal -1. What's the range? The range is now this has a horizontal asymptote of 0. So I know, looking up and down, it goes -infinity to infinity, but there's once again a break or a gap at 0. So I think we're going to choose this first answer. The range is all numbers except it can't be 0. Now, vertical asymptotes. Vertical asymptotes, you basically look at the denominator and you say what values of x would cause the denominator to be 0. Well, if x is -1, then the denominator is 0. So that's going to be your vertical asymptote. So let's see the answer. There's one vertical asymptote, and it is x equals -1. Horizontal asymptote, that's a little different. Horizontal is where you look at, compare the leading terms. So here, basically you have -3 over x. What happens as x gets huge? This whole thing goes to 0. So we do have a horizontal asymptote of y equals 0. I think there's some more questions on the next page. Oh, they ask if there is an oblique asymptote. No, there's no oblique asymptote. So you just said there's no oblique asymptote. 27, another rational expression. Looks like they're asking us to find about the asymptotes. Vertical asymptotes, once again, vertical asymptotes are pretty straightforward. You look at the denominator and say, what value of x would cause the denominator to be 0? Well, if x is -3, so that's your vertical asymptote. X equals -3. Horizontal asymptote is where you compare your leading terms. So when you compare leading terms, that means you ignore that. So you have 14x over x. The x's cancel out. We're left with 14. The function, or you can think of y equals 14. So the horizontal asymptote y equals 14. And are there any oblique asymptotes? Nope, no oblique asymptotes. All right, I think we have two more problems. Let's see what they are. Another rational expression. There's a chance we might want to factor this. Let's go ahead and do it now. I think it factors into x plus 5 times x minus 4. Actually, they ask us to factor it. So this answer here is what I wrote up here. And then what is the domain? Well, the domain, we know how to find domains, right? Since we have variables in the denominator, domain is going to be all real numbers except for -5 and 4, right? We've done that before. Let's see what kind of answer they want. So all real except -5 and 4. Right, our x lowest terms. So it's already in lowest terms. Stuff in here cancels. So it's already in lowest terms. Look at the intercepts on the graph. All right, x and y intercepts. Remember, actually the y-intercept, you said x equal to 0. Hopefully you can see 0 over -20. The y-intercept is 0. X-intercept, what values of x would cause this whole function equal 0? So you don't look into the denominator, you look in the top. What value of x would cause x squared to be 0? 0. So there's an x-intercept of 0 and a y-intercept of 0. Next question is, determine the behavior of the graph at any x-intercepts. So what they mean is, I think since it's x squared, remember that means it's going to touch the x-axis and then go back up. So the graph will cross, no, it doesn't cross. The graph will not touch but cross. That's not true. The graph will cross. Where's the graph? The graph is not going to cross. The graph will cross the x-axis now. The graph will touch but not cross. Oh, there it is. The graph will touch but not cross the x-axis. So it should be B. It will. We'll check. It will touch but not. Yeah. Determine the vertical asymptotes if one exists. Select the correct choice. So we have to go to the next page. So let me write down information on this new page. Let me write down both sort of equations. We have both x squared over x squared plus x minus 20. And if we factor it, it's x squared over x plus 5. All right. So continuing on with the questions. It's asking about vertical asymptotes. There are actually two, right? X is -5, X is 4. The function has two vertical, the leftmost. So we know it's -5 and 4. So the leftmost is x equals -5, and the rightmost is x equal 4. Determine the behavior of the graph on either side of the vertical asymptotes. If one exists, select the correct choice. This is a little tricky. So actually, we have to sort of almost like do a little sketch. So if you can imagine, I'm going to draw my asymptotes. Here's -5. And here's 4. So I have to sort of imagine plugging in values of x on either side of these asymptotes and see what happens. So if you look up here, let's say I plug in something like -5.1. So a value that's just a little bit to the left of this asymptote. What's going to happen up here in terms of the sign? Is it going to be positive or negative? Well, -5.1, this first parenthesis will end up being negative. This parenthesis is negative, 2 negatives are positive. So this is like positive. So I think that means the graph may go like that, where the graph is positive and it gets really close to the asymptote but never touches it. Now, what about on the other side? So how about if I look at like -4.9? If I plug in -4.9, this first term now is positive. This one's negative. So my guess is the way these things work, it probably may look like that. And actually, later on, we're going to find out we have a horizontal asymptote at like y equals 1. So very near to the asymptote, the left-hand side is positive. Now for this one, if we plug in 3.9, positive 3.9, this is negative. So this is negative. So maybe it's like this. And then if I go just the other side of the asymptote, like 4.1, positive, positive, positive. So maybe like that. That's my guess of a rough sketch of what's going on. Let's see if I can figure out how to answer these questions. So it says, determine the behavior. It approaches infinity on one side and negative infinity on the other. That's what it does. So on one side, it approaches positive infinity because it's going up. The other side is negative infinity. So that's part A. It approaches positive infinity on one side of the asymptote at x equals -5. This is almost more confusing. It approaches infinity on one side of the asymptote at x equals 0. On the other, it approaches in. This is very confusing, these questions. Let me see what they're getting at. I think what's getting at is for both these asymptotes, one side's positive, one side's negative. One side's positive, one side's negative. So I think the answer here is at -5 and 4, it's positive infinity on one side and negative on the other. It's a little confusing. Determine the horizontal asymptotes. If you look at leading terms, you end up with x squared over x squared. They both cancel out, which equals 1. That's why I said horizontal asymptote. It's going to be y equals 1. And then finally, determine the oblique. There's no oblique asymptote. But I think there are more questions. Here it is. Determine the points, if any, at which the graph of R intersects the horizontal or oblique asymptote. So the asymptote is in y equals 1. So what you do is you take your equation and you set it equal to 1 and you solve for it. So I'm going to take here's this equation. I'm going to set equal to 1 and I'm going to solve for x. I'm going to look at the value of x that causes this thing to equal 1. Multiply both sides by this denominator and you get x squared equals x squared plus x minus 20. These x squareds cancel out. Turns out. So the place where the graph crosses that horizontal asymptote, which happens sometimes, is when x is 20. And that's probably the question. The graph intersects horizontal asymptote at x equals 20. And then there are a few more questions. Seems to never end. Use the real zeros of the numerator and denominator to divide, determine whether the graph is above or below the x-axis by choosing a number. So we already sort of did that. So basically, we've sort of sketched out the graph. And so we're saying it's above the x-axis here and here. So negative infinity to negative 5. And from 4 to infinity. And it's below the x-axis from negative 5 actually 0 is where it's at. So here are the negative parts. So this thing really goes like this. And then the graph, which I sort of sketched it out here, looks like this here. I've already sort of done the graph. So it's going to be C. All right, now the last problem is just like that one with one difference. So I'm just going to actually skip all the other stuff, which we've just done. And I'm going to get to the one key part. So let me show you what that is. Because if you notice the initial equation, if you look at the top, the leading term is x squared, the bottom is x. So there's no horizontal asymptotes, a lot of stuff going on. But the key thing is I want to do is way at the bottom, they kept asking about, matter of fact, the next page, they kept asking about oblique asymptotes. Way down here, here's a problem where you do have an oblique asymptote. So I want to take the time to go ahead and show you how to calculate the oblique asymptote. That's the main difference with this problem. And I just want to skip all the rest because that's stuff we've done before. So an oblique asymptote, you take this and you turn it into an old-fashioned division problem. So you can think of this as the top divided by the bottom. So if you remember how to do old-fashioned division, you put the top in here and you're dividing it by x plus 3. So what you do is you say what times x equals x squared, well, x. So x times x is x squared. X times 3 is 3x. And just like you used to do old-fashioned division, you subtract x squared minus x squared, 0. 8x minus 3x, it's 5x. And then you bring down minus 9. And then you say, what times x equals 5x? Well, 5. 5 times x is 5x. 5 times 3. Now you subtract it, you get 0 minus like 28. So what you can say is, if you sort of rewrote this, you can say this thing equals x plus 5 minus 28 over x plus 3. It's sort of a crazy way to think about it. Now for the oblique asymptote, what you do is this fractional part sort of goes away, and this becomes the equation of your oblique asymptote. It's just a slanted line, x plus 5. So then for the oblique asymptote question, it has one oblique asymptote, and the equation is y equals x plus 5. And if you were looking at the graph, well, I'm not going to worry about that now. All right, so that's a lot of problems. Hopefully that'll help you as you're working through these practice test review problems. If you get stuck, you can see how I did them, and that might help.